Our modern society is absolutely dependent on orbital space, that we have this low Earth orbit region around the planet where all of these satellites and space telescopes are orbiting around it. Beyond that, you have geosynchronous orbit where a lot of the broadcast satellites exist. Very useful part of our region of the solar system. But beyond that, you're now starting to interact with the moon. You have the Earth-Moon L1 Lagrange point, and then you have orbits around the moon. And there's this vast region collectively known as cislunar space. And when you think about, say, the Deep Space Gateway, that's in cislunar space. When you have the Lagrange point, cislunar space, the L2 point, like a lot of this is interacting with the moon. And the dynamics of this region are very different from what we have in low Earth orbit, because you have these interactions between the Earth and the moon and even the sun and some of the other planets. And there's some really interesting advantages. There are these really interesting low energy routes that you can take to get from the Earth to the moon if you're willing to take time. So my guest today is Dr. Aaron Rosengren. He's an associate professor at the University of California, San Diego. He's recently published a paper looking at the history of cislunar space, going back and seeing the research that was done back even in the 1960s as they were figuring out the Apollo missions, and then considering that when we think about the Artemis missions and the different trajectories that have been taken to get to the moon, and then considering what the future might hold for this region around the Earth and the moon. So if you're interested in orbits, if you play Kerbal Space and you want to get some suggestions on some new orbits you might want to use, enjoy this interview with Dr. Aaron Rosengren. Aaron, you have been specializing in orbits and accessing cislunar space, and you just completed a fairly thorough review of the existing literature of like how we get from the Earth to the moon. What did you find?
Yeah, there is a tremendous amount of early literature. I think that's been forgotten in the present era. We now use this term cislunar, and it carries such weight, but it does not simply denote that space between the Earth and the Moon. And currently, what it's kind of, the sort of catch-all for this domain is that it's the new operating volume of the 21st century. Like, I guess, space exploration. You have, things like these low energy pathways that can get us there. And this is sort of a modern take on space highways in a way. I don't think they're very fast, but they get us there efficiently using the gravity of the sun. So, it's a very sort of circuitous route to get to the moon. And this is something that we've done. And Capstone is a mission that's ran by Advanced Space out in Colorado, and that's testing some of this navigation, autonomous navigation capabilities that we would need for that future Earth Moon economy that is being developed, and sort of at the congruence of commercial, civilian, military, and exploration.
Yeah, and that whole idea of these sort of low energy pathways, I totally want to get into that, but I, the pathways to the moon were developed, I guess, as part of the Apollo program, where they were trying to figure out how are we going to actually get to the moon. And I think one thing that I find really interesting is how orbits are almost discovered through the mathematics, where people go, well, what if we go this way or that way or this way? That it's not just like it just collapses immediately into, well, here is the obvious solution for you to be able to go to the moon. There are a bunch of ideas that need to be run through. So what was that process back in the Apollo era?
Yeah, so I mean, the history of celestial mechanics is very long, and celestial mechanics is sort of the broad, term for the study of the natural motions of objects under mainly gravitational, but also non-gravitational forces. When astrodynamics became a term, and it was coined during the Apollo era, to sort of be the engineering aspects of dynamical astronomy. No longer were the orbits of natural bodies. No longer we were confined to like the natural racetracks of the solar system. All the planets orbit in the plane of the ecliptic almost, and they have small eccentricities, which means they're pretty much circular. And now we sort of can design orbits, and we can look at now the evolution of well, if we have an orbit that's now like, let's say, inclined 90 degrees to the equator, well, what's the long-term evolution of that orbit? And these are questions that maybe they didn't ask back in like the 17th, 18th, 19th century in celestial mechanics. But nevertheless, they did study the same underlying dynamical model, and that is the what's at the basic level, the it's called the circular restricted three-body problem, and an idealized mathematical model that has been studied from both mathematical celestial mechanics and from applications. And during the early Apollo days, they applied a lot of that knowledge of celestial mechanics to these orbits. And the thing is that, the Earth Moon system is very unique in the solar system. I mean, we have a very large companion, and it's almost a binary system like Pluto Charon. And so the dynamics you can sort of think like in fluids, there's something called the Reynolds number, and high Reynolds numbers means like, you have stronger flows and things of this sort. You can think of like that mass ratio, how big the moon is as a companion, that sort of sets the tempo of the gravitational currents that we experience. And so it changed, I think, a lot of the dynamical landscape has changed from, the classical antiquity of, planetary science to these specialized orbits. The ones that we use for Artemis 2, the first time we sent humans back, to circumnavigate the moon since 1972 or 3. It's that was the same free return trajectory that was used by the late stage Apollo mission. That was found by that was the early inception of that work was by Arenstroff. He was studying the three body problem and found these interesting orbits in it. And I mean, the thing is that this problem in mathematics is not solvable, which means you have an analytical solution to tell you what's going to happen throughout all time. So there's a few ways to understand it, and you can understand the structure of the equations and maybe some constraints that structure allows to have. The other way is numerical methods, and so that's one of the things that happened during the Apollo ages. We started to have capabilities. We went from human computers to real computers and what we have now. So there are still solutions to the three body problem we don't know about and still being found today.
Right.
And that,
Yeah. And again, I find that really fascinating that it feels like it's all just clockwork motion of the planets and the moons and everything's going around. And all you have to do is just figure out what is the most efficient way to get from here to there. And the solution just pops out. But it's not. It's, as you said, three body interactions, there's chaos, long-term things are changing. And I think one of the big discoveries more recently is just how there are all these free highways to be able to get from place to place, which you mentioned about that mission earlier on.
Yeah, I talk to my students. I say, the thing about these operations in deep space where the gravity of the moon and the earth are both present, and they're both important for the evolution of these objects. If you drop something in space, low earth orbit, if you drop it near the earth, it's going to go into orbit about the earth, and that orbit's going to stay that idealized like circular elliptical path for a number of revolutions, and over time, yes, it deviates, there's atmospheric drag, there's all the things that happen, but for the most part, it's a well understood Keplerian pattern. If you do the same thing near the moon, now the moon's a little bit more clumpy in its internal composition, but you do that to the moon and similar things happen. I mean, it's going to orbit the moon. But if you drop something in that region of space between the Earth and the moon, known as the Lagrange points, well, those are unstable. We think about them as like the new, the choke points of space, but there's nothing about them that keeps things there. And they're not like the Straits of Gibraltar, as people also like to think about. Like, you have to control these regions. This is going to be the new space operations sort of central command, but it's not. It doesn't work that way in the physics. But if you drop something near those guys, well, that path of that object can go anywhere from crashing into the Earth, crashing into the moon, orbiting that point for a number of revolutions, to leaving the Earth Moon system entirely. And then it's very sensitive to how you drop it and which direction you drop it in. So it's a very different landscape. But again, a lot of that understanding was also seeded during the early Apollo days. We're just now starting to catch up to it, I think.
Yeah, and I mean, people are very familiar with James Webb, Euclid, Gaia, missions that are using the L2 point. Other stuff is using, say, the Earth Sun L1 Lagrange point, things that are observing the Earth or observing the sun. And so these Lagrange points, which are inherently chaotic and do require fuel to kind of maintain your position, yet have all of these uses. And it's a very fascinating, almost, I don't know, like you have to kind of be comfortable with the chaos of the situation and adapt in real time to where your spacecraft moves, as
Yeah,
opposed to being able to predict it.
that's a good way to put it, is being comfortable with the chaos. So each, let's say in isolation, the Earth Moon system has its own set of Lagrange points. Every three body system would have something like this. Like the most natural one is Jupiter and the Sun. There's these L4 and L5 Lagrange points, which are the stable ones, and we have the Trojan and the Greek asteroids there. And there's a whole population of small bodies, small solar system bodies that orbit in those regimes. So they're co-orbital with Jupiter. As Jupiter is orbiting the sun, 60 degrees ahead and 60 degrees behind are the Greek and Trojans, and they are orbiting with it and staying in that sort of regime. The collinear ones along the line joining the planet to its central body, so the sun, for instance, those are dynamically unstable. They're intrinsically unstable, but there are orbital paths about them that don't require much fuel to stay there. And so every system has one. You mentioned like the James Webb. The James Webb is at an Earth Sun Lagrange point, and we've had a number of missions that are at those. The what became I think it's the Themis B and C, which became the Artemis mission. And the whole name changing of everything that happens so a little bit of an interesting chaotic path itself, and how these space missions become what they are. Changes with the political climate too. But the Earth Moon has its own set of these. There's sort of like cherished zones in the three body problem, and so does the Sun Earth. What I find very fascinating, and in what I've sort of hoped to elucidate in this long sort of monograph that I wrote with my collaborators, is that the Sun Earth Lagrange point sets the whole sort of scale for what is possible for orbital motion about the Earth itself. So if you go beyond the moon, you can still orbit the Earth up until you get to those Lagrange points, and then now you can orbit those Lagrange points, or you can fall in towards the sun or fall out towards Mars.
So you could still orbit the Earth, say, I don't know, what's the L2 Lagrange point? Two and a half, is it 1.5 million kilometers from us?
Yeah, that sounds about right. I know.
Yeah, so you could be like 1 million kilometers away from the Earth and still be in orbit and not fall into solar orbit at
Sure,
that point.
sure. But it gets a little bit muddled at the I call it the translunar fringe. When you're that close to the sun, I mean, and you're not going to stay there for very long, because that's a thing. There's a number of studies and the exoplanetary research that look at, like, can a planet around another star host a moon? Because we think that the moon, our Earth's moon, is vital for life on Earth because it stabilized our climates. So we're trying to detect exomoons. That's a big topic right now. That's seen a lot of research in the last decade. Well, if you think about that, what is the boundary at which you can retain a satellite? That's a fundamental question. We're sort of unique. We have one moon. Mercury has none. Venus has none. Mars has two sort of captured asteroids, right? Phobos and Deimos. But we have one moon, and the region beyond the moon is a dynamical, like, stomping ground. I mean, it's a chaotic nightmare in terms of, like, you have the moon internal, which creates its own set of interesting phenomenon, and then you have the sun external, and those compete in a way that is I don't think has been before studied to the depths in which we did in this work.
I really think with the Artemis mission, this is having a lot of people now evaluate and consider the various kinds of lunar orbits and what it means to be in cislunar space. And we got two very interesting orbits with the first two Artemis missions. With the first one, it was out there for upwards of a month, right? Weeks, as it was sort of making these double loops around the moon. And then for Artemis 2, as you said, it did this free return trajectory very quick, done within a week or so. What are we now sort of, as we move forward and we consider, say, the return to the moon with Artemis 3, or sorry, I guess Artemis 3 is going to be in Earth orbit, but we move to Artemis 4, maybe with the landing on the moon. Maybe there is some redevelopment of the lunar gateway. How should we then look at the kinds of orbits that are being used for us to be able to go to and fro from the moon? Like, imagine we've got this future research station on the moon with landers coming and going. What does that look like?
Yeah, so from the human exploration point of view, we haven't solved the big radiation problems yet to like get to Mars. And the whole moon to Mars story is
Hmm.
sort of central to like, us going back to the moon. We've changed sort of what, I think during the Bush era it was the Constellation program, and then it became let's capture an asteroid and use that as our stomping, as like our testing ground to get to the moon again, and let's get to the moon to Mars. And it's always been this sort of objective. A lot of those pathways that we talked about in the beginning, these low energy pathways that go all the way out to the Earth, Sun Earth L1, L2, and use that gravity to sort of deflect the orbit back into what's called a weak stability boundary to get captured into a kind of lunar orbit or into a Lagrange type orbit. Those pathways take a long time, and that's not going to be done with human exploration. So you think about cargo and the infrastructure, that will be the sort of landscape of robotics spacecraft,
Mm.
a lot of these exotic missions. Now the current orbit of the planned orbit for Gateway is something called a near rectilinear halo orbit. Now, if you look at it, it seems as though, I mean, from the vantage of looking at the moon, as though it's a halo around the moon. Of course, it's a little displaced. It's 3,000 kilometers in the North Pole and like 70,000 at the South Pole. But this orbit allows for continuous view of the Earth, right? You don't want to be blocked by the moon. So a lot of that, those practical concerns come into play. So this is an orbit, though, that doesn't actually orbit the moon, although it resembles in Kerbal Space Program, either whatever that game is. I think you can design a very eccentric kind of almost polar orbit of the moon, and it looks like Artemis. Sorry, it looks like the Gateway capstone type mission, but it's not. I mean, this is an actual orbit of the L2 Lagrange point or L1 Lagrange point. And these are specialized structures that again exist in that simplified model. And then the main thing in research is, do those type of exotic orbits you find in a simpler model, do they persist? How do they deform? How long do they retain their structure when you add the complexities of reality into it? And so this is sort of the where it gets more interesting, I think, from a research.
It's interesting. So where we might have, say, the fast ships are going to carry the astronauts to and from the lunar research station, and maybe they hop on the rocket. It's a straight shot. They're on the surface in 4 days, and then there's the cargo vessels. How long would that? You get like obviously you get some kind of fuel savings, propellant savings, because you're taking this one where you're essentially relying on the sun to help keep boosting your orbit. How long does that take?
So there's two types of, like, I would say, low energy transits to get to the moon. The one that has been exploited for a number of missions, even the Grail, um, you know, uh, I think it was like a formation type spacecraft that was modeling the gravity field of the moon itself, similar to what Grace did for the Earth. That went on one of those trajectories because they're cheaper to get to, and the launch costs, of course, have gone down with the commercialization of space. But these type of missions, they leverage the sun's perturbations to get back to the moon. There's other routes to get to the moon that are, I think, even more exotic, and they could be faster too. And these leverage the fact that there are commensurabilities. This is when you have like you orbit the Earth in, let's say, half the time it takes the moon to orbit the Earth, or you orbit in a third the time. Those periodicities that happen, those can actually, you can leverage the unstable nature of certain parts of those to link them together to transit all the way to the moon. And you can do that in a month, 45 days. And so I think a lot of the infrastructure is going to be looking at they're called mean motion resonances. They've been studied for the last like 60 years in planetary science. They're a huge thing about the architecture of exoplanetary systems. And we believe a lot of things like Pluto got displaced, for instance, because it's not occupying its own its own orbit, but it's also in a type of mean motion resonance with Neptune. These are fundamental in celestial mechanics, but they're now starting to be studied in astrodynamics, and I think that that's going to enable a lot of the future infrastructure that we want and we need to have these ambitious missions and sort of a geolunar economy.
And I remember the European Space Agency did a mission, it feels like it was about, I don't know, 10, 15 years ago. I think it was called Smart
Smart
1.
one.
Yeah, and they used one of these really low energy orbits, and they had a electric thruster on it, and so it took it a month to get to the moon,
Yeah.
but at a fraction of the fuel that it would take to do if you tried to go the direct route. And I can kind of sort of imagine this future where we've got this tug that is slowly carrying cargo out to the moon. It's taking the most efficient orbit it can. It's using the most efficient energy system. Maybe it's even got a solar sail on it just to
Yeah.
help.
Say maybe a solar sail, you know?
Yeah, yeah, and that you're able to then transfer cargo, because again, I don't think people really appreciate how much energy is required. It is a mountain that you have to climb that is 400,000 kilometers tall.
Yeah, I guess so two things on that to give you an idea. So, the classical solution to go from a circular low Earth parking orbit to get to geosynchronous orbit. Now, geosynchronous orbit is like a little bit over a tenth the distance to the well, no, yeah,
It's
about
like 36,000 kilometers. Yeah, yeah,
yeah, but it's
yeah.
in the moon's at like 384,000. So it's a fraction of the distance to the moon. Now, you're talking about starting from a circular LEO parking orbit and then getting into geo and then circularizing your orbit, which takes a tremendous amount of fuel. So to go from LEO to geo, which geo has been like the sort of prime real estate of space, right? So it's kind of our communications hub. To get there, it's like 4 kilometers a second of delta V. Now that doesn't sound like much, but that's a tremendous amount. To give you an idea, it's cheaper then to go from there to send something out of this Earth Moon system than it is to bring it back down and crash it into the Earth. And this is why we've created this graveyard orbit above Geo, where we push stuff out further because it's not economically viable to bring it back. And it's actually cheaper just to send it to the moon. You can send it to the moon, crash it into the moon, or you can send it out to the Earth Moon system. It's a lot less fuel. So yeah, the amount of we measured in sort of delta V changes in velocity as required are tremendous. Now, Smart One was interesting because it had low thrust, so it's ion propulsion, so it spiraled outward. And but they also designed that trajectory where it would come through those commensurabilities I talked about, and each one of those passes, because it kind of stays in those commensurabilities for a certain time, would change its orientation naturally. And so they leverage not just the low thrust, but they also leverage sort of weak gravity assists. You can think of them as kind of gravity assists to get the orbit in the right orientation so that when it rendezvoused with the moon, it could do what it wanted to do.
Hmm. And there's also the Oberth maneuver where you can fire your thrusters when you're the closest point of your orbit around some target. So I guess you can. I don't know if they were leveraging that as well, but
Yeah, that's usually leveraged during the launch, the Oberth maneuver. But
okay.
yeah.
I mean, when you think in this sort of three-dimensional orbital perspective, and you talked about this idea of like, are there choke points or the Straits of Gibraltar? What does that sort of future of lunar space and access look like? If I could sort of, 100 years from now, look at the map of where the stuff is around the moon, where would I be finding it?
Yeah, I guess if you Google space debris now, you sort of get this picture in your mind that there's a geobelt. You can see it there, and then it's kind of I guess a kind of Taurus in space, like a space donut there. And then you have Leo, which with the rise of mega constellations like Starlink and Amazon Kuiper and other ones, OneWeb. But you're gonna you have a whole bunch of objects that are close into the Earth. That's what that currently looks like. Now, of course, that's not the scale, or else each one of those pieces of debris or satellites would be like the size of San Diego. But it gives you a picture that there's a lot of things there. Now, if you look at the traffic beyond GEO, which is dubbed by AFRL, the Air Force Research Labs, and the Space Force called it the moniker XGEO, Beyond Geo, which I'm not very fond of, and I talk about this in the paper. But this whole region beyond Geo, let's say, there's been about 170 objects in the current catalog, and so we can paint that traffic portrait for you. The thing is that unlike the Leo to Geo sort of traditional terrestrial domains of space operations, these things don't stay where they're at. So it's going to be like it almost looks if you looked at it in you plotted each one of these like a comet tail, it will just look like a ball of like yarn or spaghetti or something. These things are take the amount of space, the amount of real estate that you can orbit in is vast. And so, you think about the volumetric expansion, it's over 2000 plus of that of Geo. So it's a massive amount of space. It also it's caused some worries to, how do we do space traffic management or how do we do space domain awareness when these things are, moving with very subtle changes of your once you get out there, then, agility becomes, almost trivial.
Hmm. And then of course there'll be a cloud of things that are orbiting around the moon at various orbits as well.
Yeah, the difference for the moon is that there's no sort of natural decay mechanism, right? We learned during the Apollo era that there's these mass concentrations, and that does limit the lifetime of orbits because they become more eccentric and they eventually collide to the moon. But there is no atmosphere around the moon. It's a tenuous one. It's like an exosphere. But so if but the lifetimes of lunar orbits is actually a lot more less than the lifetimes of orbits around the Earth, like Leo to Geo. And so, in fact, if you go, most of the orbits that we've used around the moon have been low lunar orbits. These are something like 100 kilometers or less above the lunar surface, and the moon is pocked full of craters. It's got a topography that's nothing like the Earth, and so when you can in principle orbit 10 kilometers from the moon. Right, unlike you can't do that with Earth. Earth, the von Karman line, which is kind of fictitious, but the von Karman line sets the stage for maybe 120 kilometers above the Earth. You can't complete one revolution before the atmosphere sends you back down. Uh, the moon, depending on the sort of geometry that you design the orbit, you can in principle orbit for many, many, many revolutions without station keeping, without actively controlling your position in space and adjusting for those other forces. Now, yes, the moon though has a lot smaller enclave, let's say, than the Earth Moon system itself. So the amount of, orbit, like in terms of moon radii, I think it's probably like 35 moon radii. The moon's radius is like 1738 kilometers. So Earth's 6,378 or something like this. So, the amount of orbital, regime volume you have to orbit the moon is smaller, and it's more dynamical because for the Earth, the moon changes the orbits of things that are beyond Geo pretty dramatically. When you get beyond the moon, the sun starts to have its effects on those orbits. When you're orbiting the moon, though, the Earth is much more massive as a third body than the moon is as a third body to Earth satellites. So it's a different scale. So then you have a number of different dynamical things that happen because the Earth is so powerful. And so, I don't know if there's going to be like a big debris field around the moon, because, a lot of things will leave it and get into translunar or cislunar space. And then when they're there, they can do a lot of different interesting things as well.
Right. So not necessarily have the same risk of a Kessler syndrome around the moon. Stuff's a lot more unstable.
I don't presume that we could have that around the moon. We definitely wouldn't have it in Cislunar. Now, the thing is, though, is maybe the Kessler syndrome, or the idea of a runaway growth of collisional cascade. I don't think that that's something that is scary for these operations beyond Geo. What is scary is that if you have a breakup or if you have a collision, those debris can go almost anywhere. So you're sending shrapnel. The irony is that, like, if for instance, if the gateway or a satellite that's orbiting in the gateway's proposed orbit breaks up, that debris is going to hit the moon. That debris is going to come in. Maybe it's going to have some interactions with the Earth's Leo to Geo zones, and it's going to maybe leave the Earth Moon system. But it's hard to predict, and it's hard to track things that far as well. So that's the big scare. Not necessarily a Kessler syndrome like event, but the fact that these objects are going to be shrapnel that we can barely see.
Aaron, what are you obsessed with right now?
I'm very much motivated by this problem that I think nobody's really working on, and it's sort of a dynamical handoff regime beyond the moon. So we think about cislunar is, I mean, from the lexicon point of view, it should be from the Earth to the moon, but it's kind of this broader area that now denotes the whole sort of Earth Moon system that we care about right now, the sort of operating volume. But beyond that, it's such a dynamical playground. I mean, it's really hard to orbit for anything longer than several periods, and there's interesting phenomenon that have only been looked at in the solar system dynamics community that are now starting to be uh, applicable. And so I think that that's really where I get a lot of motivation at is because a lot of the questions of stability of orbits becomes a whole different problem when you get beyond the moon. Even though you're still orbiting in the Earth Moon system, you're still below the Sun Earth Lagrange point. So that's where a lot of the thrust of my research is in, and I'm also looking at some trying to recover where historically a lot of the old spacecraft have been and are currently at. So we think about like we missed the moon in the early stages. It's not that easy to hit the moon actually, and we missed it, and those spacecraft went into heliocentric space. Well, it's connected. The whole system's connected. A lot of those things are coming back, and they're kind of masquerading as near Earth objects. And they're complicating, the Minor Planet Center, which is trying to track, hazardous asteroids. And we now see these, let's say former, derelict objects now coming back, and we're thinking, well, that's what is that,
Right.
and
Is that
so
an asteroid or is that a spent
yeah,
booster?
and I think there's now a new name for these type of objects, kind of like UFOs or something. But they're just exotic paths that have finally made their way back, and so I'm studying a lot of these objects, and
Hmm.
also like trying to find out where. I mean, the Lunar Reconnaissance Orbiter has found out, like through the detailed mapping it's done, is like, oh, we see a new crater inside a crater. That's where that spacecraft launched in the 60s collided. And so, like, but we still don't know. There's probably still about 20 objects. We don't know where they're at.
Yep.
And
Yeah.
so I'm trying to find where they're at.
Yeah, they do get away from you.
Yeah, I
Yeah,
get,
that's really interesting. Awesome. Well, Aaron, thank you so much for taking the time to chat. Good luck with your research and good luck hunting down those missing objects.
yeah, thank you.
I hope you enjoyed this interview with Dr. Aaron Rosengren. Now, we have a much longer version of this exact interview over on Patreon, where we talked about the risks of impacts on the moon itself. And so we talked about flying around the moon, but often people are crashing their spacecraft into the moon at the end of the mission. This is kicking up debris. Think about the potential impact of that asteroid YR4 that could have smashed into the moon. Think about the spacecraft that are just landing on the surface of the moon and kicking regolith into orbit around the moon. All of this has an impact, pardon the pun, and something that we have to consider. And so Aaron and I talked about what are the risks, what are the kinds of effects that we might see, and how could we mitigate the dangers as we send more and more spacecraft to and from the moon. I'm going to put a link down in the show notes to access that longer version over on Patreon. It's completely free. You don't have to sign up. You don't have to pay us anything. You can just go watch that episode right now. I'm going to give you some final thoughts, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Brian Bodie, Caradon, Chuck Hawkins, Commander Bailock, Dark Finga, David Gilton, and David Matz, Enthraller Reading and Math for Toddlers, Evan.Pro, James Clark, Jerry Mattern, Jim Burke, Marcel Smith, Michael Purcell, NASA Ocean Guy, Nordspace, OneStepForAnimals.org. Please follow my nephew at VBrick6994, Ring Kaidu, Richard Williams, Sean Sargent, Stephen Found Team 49, Telescopes Canada, Vlad Chiplin, Wolfgang Klotz, Zelda Sorry, I really wanted to hear you say it, who support us at the Master of the Universe level, and all our patrons. All your support means the universe to us. So this is really interesting to me when we think about going from us tentatively exploring the cosmos around us, sending up the occasional satellite, moving into this regime where we are going to have thousands, tens of thousands, maybe hundreds of thousands of satellites in various orbits. We are going to turn space into a domain that we have done to so many other parts of our planet. We have roads, we have shipping lanes, we have aircraft lanes, and we're going to be doing the same thing with space. And I think when we consider science fiction tells us, you're flying off and space is big and it's empty. And it is both big and empty, but certain regions are actually going to become quite packed in, and that there are going to be consequences. And we've been through this before. We know how this goes, that you start out, you think this thing is free, it lasts forever, and then it turns out it's not free, it doesn't last forever, and you have to figure out a way to be able to use this common resource to get the most out of it. And that we should sit down and have the planning now and figure out the regulations and be using cislunar space, the L1, L2 Lagrange points, all of these places, so that we have maximum value and minimize the mayhem for us to be able to move forward. And the time to think about that is right now. Well, the best time was like 20 years ago, but now is the second best time. And it's great that people like Aaron are doing this work. All right, we'll see you next time.